Hello everyone, welcome back to another lecture. This time we want to discuss uh, solving logarithmic equations. That's the topic we want to discuss. I start with like easy examples and then I'm going to give you harder examples. So logarithm of x minus 4 equals 1. This is a logarithmic equation. We need to find the unknown, that is the variable x, for which left side equals right side. So in order to solve this logarithmic equation, we're going to use the definition of logarithm. We're going to say if log of something to the base 10 is equal to 1, this means that 10, the base, raised to exponent of 1 should equal to x minus 4, the argument of the logarithm, naturally speaking. So here I'm going to say 10 to the exponent of 1 equals x minus 4, from where x would equal to 10 plus 4, that is 14. So pretty straightforward kind of exercise. But the thing is that you have to always bear in mind that the answer you're getting must satisfy the equation. Sometimes our solution becomes inadmissible because it doesn't satisfy the equation. Now here, you know that the logarithm must be defined, which means that x minus 4 must be a positive value, not even equal to 0. So we know that here, x minus 4 must be positive, and that is the restriction we have. From here, we can conclude that x has to be greater than 4, which is the restriction involved here. And the answer we got was 14, which is way bigger than 4. Therefore, the answer is okay, and it is admissible, and we have no problem with this solution. And even if you plug it in the equation, 14 minus 4 is 10, log of 10 base 10 is equal to 1. You see that clearly it satisfies the equation. This one, again, similarly, we can say the base of the logarithm, which is 10, okay, it's a common logarithm, raised to the exponent of 2 equals 2x minus 3. That means 100 plus 3 is 2x, right? And then from there, we can get 2x equals 103, or x would be actually 51.5. And we know that 2x minus 3 has to be positive, meaning that x has to be greater than 3 over 2. And of course, 51.5 is way greater than 3 over 2. So that is an admissible solution. To make the question interesting, I can change the base to something else. Let's say I change it to 5. So if I have room, I can write it here. I will make room here. So imagine if it was log base 5 of 2x minus 3 equals 2. In that case, instead of saying 10 to the exponent of 2, you would say 5 squared equals 2x minus 3. So 25 equals 2x minus 3. 2x would be actually 28. And from there, x equals 14 would be the final answer for this exercise. And it would still be admissible because 14 is greater than 3 over 2, which is 1.5. Okay, so these are relatively easier examples. Now we'll try a more complicated scenario. Log of something plus log of something else equals 1. So whenever I see the sum of two logarithms, believe it or not, it reminds me of the product law of logarithm. Okay, we know laws of logarithm in and out by now, or that is my assumption at least. So log of m plus log of n is going to be log of m times n, the product. So I can write the left side as log of x minus 1 times x plus 2, okay, and that is equal to 1. So log of something to the base 10 is equal to 1. So using the definition of logarithm, we're going to say 10 to the exponent of 1 equals that product, which is actually x squared plus x minus 2. If you expand it, if you multiply the two binomials and collect lactams, that's what you're going to end up with on the right-hand side. So we're going to transpose 10 to the other side, so we get x squared plus x minus 12 equals 0. We ended up with a quadratic equation, actually. We can solve quadratic equations by factoring or by quadratic formula, whichever method we feel like it. In this case, it is easier to solve it by factoring because it's easy to find two numbers that add up to 1, but the product is negative 12. The two numbers are 4 and negative 3. Quickly, we factor the quadratic trinomial, and then we're going to apply the zero product property. I'm going to say either x plus 4 is 0 or x minus 3 equals 0, from where I get two solutions, x equals negative 4 and x equals 3. But I had warned you before. I said, be careful. You have to make sure that your answers satisfy the logarithmic equation. Otherwise, maybe one of the solutions would be inadmissible. Now, we have two logarithms here, clearly. And one thing I want you to always consider is that both of these logarithms to be defined to begin with. So I want to say that x minus 1 has to be positive in order for the first logarithm to be defined, and x plus 2 must be positive in order for the second logarithm to be defined. So this implies that x has to be greater than 1 and x has to be greater than negative 2. So these two conditions must be satisfied and not satisfied separately. Simultaneously, they have to be satisfied. So basically, from this condition and that condition or restriction, we have to come up with a sort of common, restriction here. If x is greater than 1, or it's supposed to be greater than 1, in order for the first logarithm to be defined, and the other one says x has to be greater than negative 2, well, what is the conclusion here? What's the common ground here? I would say if x is greater than 1, then automatically it's greater than negative 2. Think about it. Think about it. It's so logical. So we're going to say x has to be greater than 1. If x is like 12, then obviously 12 is not only greater than 1, but also greater than negative 2. But if x is greater than negative 2, which could be 0, then it does mean that x is greater than 1. So you have to take the intersection of these two intervals, basically. So x greater than 1 would be the intersection. So we have peace of mind that if x is greater than 1, then both of these logarithms are defined, in other words. Now we look at our answers. X equals 3 is the one solution we got. Is it greater than 1? The answer is yes. Therefore, it is an admissible solution. X equals negative 4. Is it greater than 1, satisfying the restriction? No, it is not. Therefore, this solution is inadmissible. Okay? These kind of roots are known as extraneous roots. Okay? Extraneous roots are roots that sometimes appear in different equations, and they don't satisfy the original equation. So we don't count them as admissible solutions. If you plug in negative 4 right in here, it's going to become log of negative 5, which is totally undefined. Okay? So obviously x equals negative 4 is not an admissible solution. But if you plug in 3, log of 3 minus 1, which is log of 2, and over there we're going to have log of 5. So log of 2 plus log of 5 would be log of 2 times 5, which is log of 10, and log of 10 base 10 is equal to 1. That's the left-hand side. But look at the right-hand side. It's also equal to 1. So that means the left side equals right side. So this answer actually satisfies the equation, but the other solution is not. So that's called an inadmissible root. We don't accept it. Extraneous root, it's called. So we have only one solution for this logarithmic equation. Sometimes if there's a multiple choice question and it says option A, it says x equals 3. Option B, it says both. Option C, it says negative 4. So which option are you going to select? You're not going to say 3 and negative 4 both are the solutions. So we're going to say only option A, which means x equals 3 is the only real solution for this logarithmic equation. This is another one, but this is a little bit different because when you transpose the logarithm from right side to left side, see what happens here. We get log of x plus 4 and then minus log of x minus 2 equals 9. So here, unfortunately, I cannot do what I did before. I can't use the product law of logarithm because I don't have a plus sign in between the two logs. I have a minus sign in between the two logs. Therefore, we use the quotient law of logarithm. So this becomes log of x plus 4 over x minus 2, okay, equals 9. All right. Now, the base of the logarithm, I can, if I just leave it as it is, base is 10, it's going to be a huge number. So I'm going to change it to perhaps maybe 2, if you don't mind. So I'm going to change the problem. I'm going to put the base of 2. So now we're going to say 2 to the exponent of 9 equals x plus 4 over x minus 2, right? And 2 to the exponent of 9 is actually 512 if you use a calculator. And that is x plus 4 over x minus 2. So doing cross multiplication, 512x minus 1024 equals x plus 4. And then rearrange it terms, 511x equals 1028. We end up with a fraction as the answer, which is, of course, okay. So 1028 over 511. I don't think we can reduce this fraction. That's final answer. But is it admissible or not? We don't know. We have to check. We have to check the restrictions. Here, just like before, I'm going to say x plus 4 has to be positive, and also x minus 2 has to be positive, because both of these logarithms need to be defined. So that means that x is greater than -4 and x is greater than 2. Now, what is the common ground? What is the common intersection of these two intervals? The answer is x greater than 2, obviously, because if x is greater than 2, automatically it will be greater than -4 as well. So now, is it true that this number we got is greater than 2 or not? Let's check to see. Roughly 1028 divided by 511, it is equal to 2.011. So this is roughly 2.011, and we see that it is actually greater than 2, and it would not create any issues. Both of these logarithms are defined, and it would satisfy the equation. So it's an admissible solution, basically. Okay, so we did a few examples. This is just another one. Logarithm of cube root of something equals 2/3. So how are we going to deal with this one? Well, the first thing I'm going to do would be expressing this cube root in the form of an exponential expression. So x squared plus 48x to the exponent of 1/3, okay, log of that equals 2/3, and then 1/3 becomes a coefficient for the log, okay, and then we see that if you multiply both sides of the equation by 3, you get rid of the fractions on either side, so you get log of x squared plus 4x equals 2, but then the base is 10. This is a common logarithm, so 10 squared is going to be 100, obviously, and that is equal to x squared plus 4x. Again, we ended up with a quadratic equation. So when you solve this, you end up with a quadratic equation like this. Now, we need to solve this to see what the answer is. The question is, can we factor this? Can we not factor this? That is the question here. I just noticed something, and that is this was 48. I copied 4, so I knew that something somewhere must be wrong. So that was a 48 actually. It's good that I catch it. So x squared plus 48x minus 100 equals 0. Now this can be factored actually, because 50 times 2 is 100, and if 50 is positive and the 2 is negative, the product will be negative 100, but when you add them up you get 48. So this means that either x plus 50 is 0 or x minus 2 equals 0, which means that either x is equal to 2 or x equals negative 50. So as I said, we have to check to see if these answers are satisfying the equation, or if not, then they're going to be called an extraneous root. So we plug in negative 50 and see what happens. If you plug in negative 50 and you square it, it's going to be 100, and added with 48 times negative 50 using a calculator, we end up with a cube root of 100. So cube root of 100. So if you sub in negative 50, you get log of cube root of 100. So this is if x is negative 50, and that's equal to 2/3. Now cube root of 100 would be log of 100 raised to the exponent of 1/3, and that would be 1/3 of log of 100, and log of 100 to the base 10 is going to be 2, and sure enough, left side will be 2, and we see that right side is also equal to 2/3. So the answer is yes, this is an admissible solution. X equals negative 50 satisfies the equation. And if you try 2 squared is 4, and 2 times 48 is 96. 96 plus 4 is 100. So again, cube root of 100, that's what we're going to get. So if x equals 2, once again, we get log of cube root of 100, which is equal to 2/3 as we calculated earlier. So we see that both of these solutions are actually admissible. So sometimes, as you see, both solutions are admissible. Sometimes one of them is admissible, the other one is inadmissible, depending on the case, of course. Okay, and I can come up with examples where the logarithmic equation does not even have any solution. We can even come up with some sort of equation like that. Okay, so if you have, I hope you have understood everything and you will continue practicing. Thank you for your attention.